When I was a student, I had a tough time grasping the concept of internal reversibility for some processes that overall were irreversible. Um, and so I found that to be a very difficult concept to understand. So I'd like to take a clip out of your textbook as well as give you an example to illustrate internal reversibility as best I can explain and understand it. So this little short video is entitled Internal versus External Irreversibility. And so I'm trying to sort of put it all together, but I think we're going to start with a clip right out of your textbook. Yes, and here it is. It says, there's a subtle key point that's kind of buried in your textbook, and that's identifying where is the irreversibility for, as engineers, where are we going to model the irreversibility for a certain proposed process? And so I've clipped out section 5.3.4 that's entitled Internally Reversible Processes. I'm not going to read that text to you because I think maybe you could scan it real quickly. It does talk about a process where there are no irreversibilities present within the system. And so, probably what's going to come to your mind is, okay, I think I got that. There's no friction within the system. That makes sense, right? No unrestrained expansion within the system. Got it. But the hard part is wrapping your head around heat transfer across a finite temperature difference. And so my remarks here are particularly related to how we deal with processes that involve heat transfer of any type, and then how we model processes as internally reversible. And so here's an example I'd like to cite, and this is a little bit, this is out of your book. Your book talks about this, so this isn't my independent thought, okay? And the example has to do with condensing water vapor, condensing saturated vapor into saturated liquid in a copper pipe. Okay, and so I've taken a little bit of a picture of a copper pipe, and obviously this is an open system, one inlet, one outlet. Let's say it's steady state, steady flow. So you could be kind of comfortable about this. If I gave you mass flow rate, you could, with the given information, saturated vapor at 125 degrees C, coming out as saturated liquid, it would be dribbling out of the pipe, saturated liquid at 125 degrees C. So it's condensing at a constant temperature. You could calculate the heat transfer, couldn't you? The copper pipe is not lifting a weight. There's no work involved. There's no shaft coming out of the copper pipe, okay? And so what's going on? So heat would be rejected from the steam, wouldn't it? Obviously, Q dot N would be less than 0. So we could label a sketch Q dot into the surroundings. Q dot into the surroundings at 25 degrees C is some positive number. Q dot into the steam is a negative number of the same magnitude. Okay, we'd get so many kilowatts of heat transfer rate. And so what I've labeled in my example is, what does your common sense tell you the copper pipe temperature? If you could, you shouldn't, right? Not at 125 degrees C. You'd burn the heck out of your hand, right? Because it's boiling water is 100 degrees C. So you would severely burn your hand if you touched that copper pipe. But your common sense tells you that copper pipe, if we really did this, the surface temperature of the copper pipe would be darn close to 125 degrees C. It would be damn hot, right? You know it wouldn't be 25 degrees C. So the copper pipe is transferring heat into the surroundings, and that's irreversible, isn't it? Because the copper pipe is 125 degrees C. Heat transfer across a finite temperature difference. The temperature difference is 100 degrees C. that's where the irreversibility is. And so as engineers, that's where we're going to model the irreversibility of this process at. It's the irreversibility is between the copper pipe and the surroundings. Clearly an irreversible process. Now, if you're a molecule of H2O and you're getting condensed from saturated vapor to saturated liquid, you don't really know what's going on in the surroundings, right? You can't see outside the pipe. It's copper pipe. You can't see outside. All right. So if you're that molecule of H2O being condensed, you're being condensed reversibly. So that's my example. So you're being you're being condensed at constant temperature in a reversible way because the copper pipe is absorbing energy from you at 125 degrees C. Your temperature is 125 degrees C. So you're exchanging energy with the copper pipe, but it is reversible. It is reversible heat transfer. So that's my story, and I'm sticking to it. And that's the best example I can give of an internally reversible process, the steam, with external irreversibilities. Okay, let me try to depict it. So this example is internally reversible and externally irreversible. So I'm going to try to draw it again, try to drive my point home. Here's my copper pipe in cross section, the little brown pipe. Okay. I've got saturated vapor coming in, saturated liquid coming out at 125 degrees C. The pipe surface is 125 degrees C. That's your common sense. It's copper, very conductive, right? Okay, extremely conductive. All right. So the process inside this pipe is reversible. Okay. However, the process outside the pipe that I'm depicting as my red arrow is irreversible because of heat transfer across a finite temperature difference. Okay, so that's another way to look at it, maybe simpler. I've tried to depict it two ways in sketches just to try to get your wheels turning and trying to get you a little more comfortable than I was early on, understanding internally reversible and externally irreversible. Okay, so that's my story, and that I offer that as an example for you to think about. Okay. And I see in my text box, I said heat transfer across a finite dt. Shame on me for not changing that to delta T. The process is externally irreversible, but we will model the inside the pipe as internally reversible. Okay, 5.3.4, another screenshot out of your book. And that is that, so your textbook in chapter 5 says, remember how we were dealing with that word quasi-equilibrium in chapters 2 and 3? Remember that? Chapters 2 and 3, quasi-equilibrium, hard word to write out. Well, now we're switching to new jargon, and we're going to call that internally reversible. Quasi-equilibrium. And how did we, back then, how did we describe quasi-equilibrium? We said no friction, no unrestrained expansion, that type of thing for slowly at all points during the process. It was the system was in a state of equilibrium. And so now we're switching over to new jargon. We're going to call it internally reversible. And that's kind of important. I didn't label it as important, but kind of important. Section 5.3.4 for you to have a look at and just dissect a little more. But it wouldn't be, let's have a reminder of processes that are internally irreversible. So no getting around it. So these examples are clearly irreversible inside the system. Okay. Unrestrained expansion, that is internally irreversible. Transforming heat into work, in other words, baseboard heater, irreversible. Friction, internally irreversible. I didn't show that. Lost opportunity to do work. We shove a weight off top of a cliff, but we don't extract any work. That's internally irreversible. Mixing, combustion, these are all examples of processes that are definitely irreversible. It doesn't matter where you're going to put the irreversibility. By golly, they are irreversible. Those are irreversible processes. Okay, so let's recap. It says, although a process may be irreversible, it may be considered internally reversible and externally irreversible. And the best example of that, I'd say most commonly occurring there, is the heat transfer process. Okay. Remember, not all irreversible processes can be modeled in this manner. So that was my screenshot of the ones that were like, no way, you can't pretend like it's internally reversible, where there's friction, where there's unrestrained expansion. Okay. And last bullet, I think I made my point. Internally reversible and externally irreversible processes, they usually involve heat transfer. So that's it. That's a quick little note about internally reversible processes. I hope that helps you, that example problem helped you get kind of comfortable with that jargon. And also remember then that also the clip out of the book, it says quasi-equilibrium. We're changing that jargon now to internally reversible.